by David on Co-Monads.
Okay, thanks. Okay, can everyone hear me? Yeah, cool. Okay, so this is an outline talk. I have a slide on motivation, why we might be interested in co-monads. Then I'm going to start by looking at the theory, which is not always the best way to start with new concepts, I admit, but I'm going to look at how they're kind of related to monads, so hopefully it'll make sense. Then show some examples of co-monads, some applications, things you can do with them, look at a few other things after that. Okay, so motivation. Monads. Is everyone here familiar with monads? Yeah, and he is good. Okay, so monads, about over 20 years ago, they were recognised as being something that was quite useful from category theory. It turned out to be useful for functional programming, to all sorts of things from I/O to non-deterministic programming, to managing state and other sorts of side effects and things. Now, category theory has a dual concept called the comonad, which most people, even if they know about monads and use them a lot, maybe haven't even heard of comonads, or if they have, they don't know what to do with them. But, well, since category theory said monads could be useful, maybe comonads are as well. So, a little bit of intuition about what you might use them for. So, monads kind of encapsulate or abstract the notion of an effectful computation of a value. Comonad abstracts the notion of a value in a context. And it's all right if you don't understand that now, but we'll have a look at what that means. And this is another quote that I found helpful. So whenever you see large data structures pieced together from lots of small but similar computations, there's a good chance of dealing with a comonad. And we'll see a bit about what that means too. Okay, so the theory. Okay, so what is a comonad? All right, so comonad is just a comonad in the category of ender functions. Okay, that makes sense. We can all go over now. Or if that doesn't help, then okay, so it's the category theoretic dual of a monad, as I said before. What does that mean? Well, it means it's a monad with all of the arrows reversed. Okay, let's see what that means. Okay, so first of all, both monads and comonads are examples of a simpler concept called a functor. Probably familiar with the definition of functor in Haskell. So it's something that a data structure that has a function fmap takes an a to b and returns a function that takes an f of a to f of b. So it's kind of lifting a function from basic values to functions over the functor data type. And interesting to talk about duals of concepts in category theory. The dual of a functor is a functor. And the reason for that is if you reverse those two arrows that are coloured in red there, you get the same type. Yep.
Why don't you reverse the black arrow?
I will explain that later, but
sure.
The short answer is that some of the arrows represent morphisms in the category, and some of them are just Haskell function arrows.
Good answer.
But yeah. Okay, so this is what this says. A monad is a functor, and a comonad is a functor. I'm going to show the definition of monad and comonad side by side so you can see how they compare. The definition of monad is not the normal one that we see in Haskell, but it's kind of rearranged it a bit to make it more helpful for the talk. So normally, for example, it doesn't have the functor constraint on there, but I think that's going to be changing soon. The other thing to note is we write the convention is you write variables representing a monad and M, and they use a W for comonad because it looks like an upside down. Okay, so monad has a function return, which takes an A and gives you an MA. The dual concept of that is a function called extract, which does the opposite, takes WA and gives you back an A. So you can see that we've swapped around the direction of the red arrow. The other function that monad has is bind, which you can see, I've written it this way around, which has the arguments flipped from the way it's normally used. So you can see how it corresponds to fmat. So fmat is just an A to B, but bind takes an A to NB as a function. Now otherwise the type is the same as the type of fmat. The corresponding function for comonads is called extend, and it has the arrows flipped. So the function here that takes a WB to an A. And the other function monads have a join, which can take an M of M of A and collapse it down to an MA. And comonads do the opposite and have a duplicate function that takes a WA and gives you a W of W of A. And also, you don't need to supply definitions for all of those because you can define join in terms of bind and bind in terms of fmat for join, and similarly for comonad you can define duplicate in terms of extend and extend in terms of fmat and duplicate. So you only have to provide one of those two, and the other one will use the default definition from the class. And this is the probably the more familiar form of the bind operator, which is just with the arguments flipped around, which makes it more convenient for actually using. And the way you write the comonad version is like that.
It looks like monad one flipped around.
So sort of tricks like that. Okay, so a couple of other things to observe. Monadic values typically produce an effectful computation. So you have something that is given an A, it'll give you a B and do some other stuff as well. And comonads, it's the other way around. So you have an A, but you also have some context around it given by the W, and you use that to produce a B. We have laws, the monad laws here. So left identity, right identity, and associativity, which is what makes G notation work and makes them easy to reason about and all that sort of stuff. The equivalent laws for comonads turns out to be identical. If you replace return with extract and bind with extend, you get the same laws. Which is not that surprising. I've got a slide later on to explain why that is, but it's basically because they're both categories. And these are really just category laws. Okay, some examples. Start with the kind of fundamental, I guess, monads that are you see all the time in Haskell. So the reader monad here, which is just adds an environment to your computation. So basically, you're adding an extra argument of type E to whatever you're doing. There is actually a reader. So there's a reader for comonads as well. Instead of a function, it's a pair, a tuple, and extract just gives you the second argument, and extend just returns, well, keeps the first argument the same and applies.
I normally would have thought that a product would be a dual to a sum, but here it's a dual. A function, I'd expect them to be adjoint, but not dual.
It's actually because you are just turning the arrow around. If you think about the uncarried form of the reader monad, you would add an extra. So you could, instead of having an E to A to B, for example, which is what the function reader monad would be, you could have a tuple of the A to B, and the comonad just flips that around. So does that make sense?
Sure.
Yeah. And the writer monad, there's a dual to that as well. And the interesting thing to note is that the co-writer monad, which is also called traced in Haskell packages, is the same type as the reader monad, and the co-reader is the same type as the writer.
Does that make it redundant?
No. It means that they're dual. You can see there's kind of a duality there between readers and writers, and between monads and comonads. So it's
Is the co-writer left adjoint to the co-reader as well?
I think I read that somewhere, but I don't know if category theory to say that's actually true. Yeah. Okay. Okay. State monad, I'm not going to go into the detail of that, but basically you have a function that has an extra state that you pass in and get out as a tuple. And the store, which is the comonad version, instead of having a function from S to a tuple, you have basically a pair with a function from S to A and an S. And the main reason, I think, well, one of the reasons store is interesting is because it can be used to implement lenses. It's not the way lenses are implemented now, but you've heard the saying that a lens is a co-algebra of the co-state comonad. So this A to something of A is just a co-algebra. So store is the co-state comonad. Sounds good. For example, this is a stream type, which is just an infinite list. It doesn't have a nil case. Obvious definition for the F map, just applying F to every element in the stream. Extract just takes the head element. So extract is the head element. Duplicate is the tails function. Is it in Haskell is the tails function, which gives you all of the tails list. So that's basically what it's doing. So you can see that the first argument you get back is x's, which is the whole stream. And then you've got recursive call, which works on the tail, and so each new element will be the tail of the preceding element. Extend. So giving you a function f, the extend will extend it by applying it to all of the tails of the stream, the new stream. And So if you compare definitions of extend and fmat, they're almost the same. The only difference is that extend passes f the whole stream, whereas fmat passes the first element. So means that when you want to do something with the stream that requires the whole stream, you've got it all there rather than just dealing with one element at a time. And each call to the function f gets the whole tail of the stream from the element that it's processing onwards. Another example of comonad is the list zipper. Does everyone know what a zipper is?
Maybe you should do it all of them.
So a zipper represents, well, this you can think of it representing a list plus a pointer into that list or a cursor or something. And you can move around in the list. You've got the A element up there, which is like the element you're focused on at the moment, and then the first list is everything to the left of that A, and the second list is everything to the right, and you can move around the list using these left and right functions. So the functor instance again is just apply everything we can. And the co-monad instance, so I've got this helper function iterate one, which takes the uses iterate, but just ignores the first result that's returned. So zipper transforms the data structure into the focus and means it's stepping around the structure. Extract just returns the focused element, which is what we saw. And duplicate returns a zipper where every element is itself a zipper focused at the corresponding place in the original zipper. And extend is kind of like fmat, but instead of having access to just one element for each call to the function, you have access to the entire zipper focused at that particular element. So you can move around if you want to get elements to the left and right. The one you focused on, you can do that. And this is different to the stream comonad. With the stream comonad, each call to the function in extend only had access to the tail of the stream, but here, because we can do both left and right, we can access the whole zipper. And it turns out that every zipper is a comonad, so zippers for trees and all sorts of other things are all comonads. Another example is an array context. So the array there is just normal Haskell array type with the index I, and we just add an extra value to say we're focusing on a particular index. Fmat just fmats over the array, and comonad here. So basically, this C array type is kind of like a zipper for arrays. You have a focus, and you've got access to your array, so you can move around it. Extract returns the focused element, and extend, you get the whole array through the zero function. You get the whole array passed to F, but with a particular element you're interested in as the focus.
Where's duplicate?
Um,
Let me define.
Oh, right.
yeah, just replace the F with AD. Okay, so here's a typical application you often see when looking at comonads. So everyone familiar with the one-dimensional cellular automata and Wolfram's rules? Yeah. So this Wolfram came up with this encoding scheme for describing all of the one-dimensional cellular automata where you've got access to the elements to one element to the left and to the right of the cell you're interested in. And they're encoded using that word 8 there, and this function just decodes it and returns the result as the ball. This code here just takes in the ball number and prints out the result of running it 20 times. The main interesting bits are you've got your initial starting point here, which is you've got your focused element as true, and you've got infinite lists of false going in both directions from there. And the other bit is this last line here, where so we use the extend function to extend the rule. So instead of just returning a Boolean, it returns a new zipper. And we can just iterate. So each iteration will be the next step in the automaton. Actually have, if I can get this to work, I can show you an example of this running. So the most famous rule is 110 because it gives you the most interesting result. And, the other rules like 30. So I guess the main thing is that you only have to write a rule for getting the result of one cell in the automaton, and then the extend will extend that so that it applies it to the whole automaton, gives you back a new, or using a zipper instruction, yes, it gives back a new zipper, which you can then iterat on to keep getting more results. So each line in that output I showed you was one result from iteration, one iteration. We can also do a two-dimensional automaton. So we just create a two-dimensional zipper by just having a zipper of zippers.
Yo, dog.
Yeah. And I'm not going to go through that, but that's how you define the comonad for it. And we can use it to implement game of life. So we've got just a function to count how many blinker. Steady state.
Either.
And I can share the code to do this with you afterwards as well, like. Here's an example from image processing. So you could use your array type to represent an array of floats and do a plus operator, which is used for like edge detection algorithms in image processing, that sort of thing. So we have just a simple rule here that takes the array of the particular focus point, and it uses its 4 nearest neighbours plus the value itself, which is this on the bottom here. That function there just it's just an array index lookup with a bounds check, and it returns 0 if it's outside bounds of the array. So again, we apply the extend function to that. Then rather than just getting a single float back, we get a whole new array back with the Laplace transform applied to the whole array. And then we pass that on to further processing steps if you want to. Either the same thing again or something else. This is an example of how you might use the co-reader, also called the environment comonad. It has ask and local functions, which basically do the same thing as the ask and local from the reader monad. So ask just gives you back the element from the environment, and local creates a new environment for a local computation. One example of that is you can use it to save your initial value if you want to do something and be able to get back to where you started. You put the initial value into the environment, do whatever you want, and then you got the initial value back. Afterwards, you just call ask and put it back. It's not a very realistic example, I suppose, but yeah. Some other applications in signal processing using streams. There's a few people saying that comonads should be good for functional reactive programming, but it doesn't seem anyone's actually implemented it. Whether they have that, I couldn't find it. There's just lots of mentions saying, yeah, this should be exactly what you need. But that sounds familiar if you know much about functional reactive programming. It's an area that seems to have been very promising, but hasn't really got the results that we expected. This is good. Stand over here. So this is from a blog post by Gabriel Gonzalez, who likens comonads to some concepts from object-oriented programming. He shows how you can do things that are similar to the builder, iterator, and command design patterns using the co-writer stream and store comonads. So I've got a link to his blog post at the bottom. You should have a look at it. It's quite a good read. But I won't go into more detail with those. Okay, so that's some applications. Does anyone have any questions at this point? Cool. So just a few other things to look at. So with monads, Haskell has the do notation. Other languages provide special notation, like F# and C# and so on for monads. So the question is there something similar for comonads? This is really still an open question. There's 2 proposals that I'm aware of at the moment. Both kind of have their pros and cons. There's just examples of how you would write some comonad code in each of them. So on the left, so I've got got two examples there. On the left is just the understood code using extend, and that's how you write it in the two different styles. So Gonzalez, I mentioned that he's trying to like a comonads to object-oriented programming, and he even adds a special this keyword. So so you can see that here I've called that the argument is lambda this, and you can actually include this as a keyword inside your expression over here, and it will transform it to use that argument. Whereas the other approach, you have to do it explicitly. So this is kind of neater if you want to write in that sort of style, but if you want to just sort of chain functions together, then this style you have to explicitly add to this, but this one you don't. And the other thing, so this is, this one's supposed to look like object-oriented programming, and this one kind of looks a bit like cross-between do notation and arrow notation, but not quite. So it's still, the jury's still out about which one's the most useful or whether there's something else better.
I'm pretty sure Overton and Mycroft are made up names.
No. Well, not fortunately. Definitely not. So transformers. We have monad transformers. So a monad transformer is something that will lift a monad of type MA to something of type TMA, where TMA is also a monad. So this is using for layering stacks of monads like readers and writers and state and so on top of each other. That extra functionality. And of course there's a dual concept called a comonad transformer. Instead of a lift, it has a lower function which takes the TWA and gives you back a WA. That's the flipping the arrow again. There are 3 examples on package in the comonad package, and they're the reader, writer, and state examples. They call them N, store, and traced, but they're basically analogous to the reader, writer, and state. So you can say you've got a stream monad, you can add a reader on top of it, or whatever. Now we looked at free monads a few months ago.
Can you leave the comonad in the monad? I'm not sure why I want that, but I did. What does iteration be like? It's not lift, it's not lower, it's not.
There are certain pairs of monads and comonads where you can write a distribute function which distributes one into the other, and what you end up with is something very similar to an arrow. I can give you some links to some pages on that. Okay, so this is the free monad which we saw a few months ago, and there's a code-free comonad. So the free monad the data type has 2 choices, pure or free. With the comonad, instead of having a sum type, you've got a product type. So yeah, the A and the other rolly thing is the same, but you're haven't got a product of that with the pure thing rather than a sum type. And the other interesting thing about them is so the idea is you plug in different functors to get different functionality from your code-free comonad. If you use the identity functor, you just get back to the infinite stream that we saw earlier. If you use a maybe, then you end up with a non-empty list. And if you use the list functor, you get a rows tree. this is the bit with the arrows. So this is a bit going a bit more into some category theory. So every monad defines what's called a Kleisli category, which is with the return function of the monad being the identity of the category, and this sort of fish-like function here, up here, being the composition operator for the category. And comonads form what's called a co-Kleisli category with extract as the identity, and this function here as the composition operator. You might wonder why we care about that. First of all, it makes it easier to see which arrows you're flipping around. It's the arrows that represent the morphisms, I guess, in the category. So the actual arrows of the category. And the other thing is it makes sense of what the laws. So these are the monad and comonad laws rewritten in terms of those Kleisli categories, and you can see they're just exactly the same as the category laws, which is the ID function is the identity, left and right identity, and that the composition is associated.
So monads and comonads, are they categories themselves?
No, they. I don't think so. No, they're-
Monads can't even compose properly.
So you need to use the Kleisli category for composition. But that's basically just adding a function argument. And that's all I've got to say. I've got a list of links to some more interesting reading there. I'll send you out a link to the slides, to the list. Any more questions?
Sure. What inspired you to look into comonads?
I guess a few blog posts I've seen recently mentioning them, and just wanting to know more about them. Kind of interested in that. Also from the FRP, I've been kind of interested in that for a while, wanting to see whether these are any use, and I read that they should be, but as you saw, I didn't really get very far with that investigation. Yeah, just something interesting.
Is there like a pithy analogy that can be used for intuition? Like a comonad is like a co-burrito or something?
Yeah, co-burrito. Yeah, I haven't seen any. The comonad tutorials aren't quite as popular as tutorials.
I think you need the Co-Monad tutorials graph.
Yeah.
What's your favourite application of comonads?
I think using them with zippers is probably zippers are obviously useful data structures for dealing with immutable types and navigating around them, and the comonad stuff just adds an extra layer of functionality.
What does the co and comonad mean?
It means it's the dual, basically.
So what's the co-concept for applicative functors, or are they self-dual as well?
Yeah, I think they self-dual. Monads are, so comonads are also applicative functors.
There could be a whole blog post on that.
These two. Good, awesome.
All right. How hungry are people feeling?